Okay, now we're going to practice conservation of energy using more problems. Let's take a look at the problem on the same PowerPoint 11. Now this, the question on slide 6. Okay. So actually we have seen this problem in circular motion, right? A ball attached to a string and then moving in a vertical circle. So what are we finding in this question? What is the minimum speed of the ball at the bottom to complete the circular motion? If you still remember, we actually figured the minimum speed of the ball at the top to complete the circular motion. How do we figure that out? Let's review that. So I know that in my experience, right, we learned you can do the experiment. If you want to move a ball with the string in a vertical circle, you need to move it at a certain speed, right? If you swirl it with a very small speed, it's not going to reach the top. So how did we find the minimum speed at the top? That's what we did in circular motion. So what we did was this. We drew a Fourier diagram of the ball at the top. Gravity down, tension also down toward the center, and then this is the center. And then, because this is the center, there must be a centrifugal acceleration toward the center. Right. But I'm not going to draw the centrifugal acceleration on the Fourier diagram. That may confuse me, right? I only have two forces on this object. So let's set up Newton's second law. That's what we did. If you set up Newton's second law, because all the vectors are down, so we can just say this is my positive y direction. So I don't need to deal with a lot of negative signs. Then what did we do? We set up Newton's second law in y direction. So net force in y direction must be equal to mass times acceleration in y direction, right? And then how many forces in y direction? Tension plus gravity, right? These are the two forces in y direction on this ball at the top. What is the acceleration in y direction? Well, it's not moving in y direction, so there's no normal acceleration, but the centrifugal, because it's in circular motion, the centrifugal acceleration is toward the center. And now I call this direction positive y direction. That is the AY I plug in, right? That's what we did. So I'm not going to plug in a number. I'm just going to use the centrifugal acceleration equation. And then how do we figure out the minimum velocity at the top in order to complete the circle? If you want the ball to complete the circle, to reach the top, you want this equation to be true at the top. And then if you reduce the speed on the right a little bit, like you do the experiment, you want to find out the minimum speed for the ball to reach the top, you can reduce the speed a little bit, right? Every time you repeat this experiment. But this equation must be satisfied at the top, always, if it's going to make this circle. So the value on the right-hand side, even though you don't know the numbers, but the value on the right-hand side is going to get smaller, then this value on the left-hand side must get smaller as well, so that this is still an equation, still true, Newton's second law. And this gravity cannot get smaller because it's mass times 9.8. Both of them are going to be constant. The only thing that can get smaller is the tension. And tension can get smaller, right? The tension in the string, you can't predict it. It depends on how tight the string is stretched. So this guy actually can vary from 0 to some value, a maximum value. So every time you reduce the speed, you want the ball to reach the top, the tension is going to get smaller, a little bit smaller, automatically. You don't have to do anything, right? Because this law is always true. Then you're going to keep reducing the speed, the tension is going to keep going down, going down, going down. So the minimum speed at the top occurs when the tension has reached the minimum. And then what is the minimum value of a tension? I just said that, right? The tension in a string can always vary from 0 to some maximum value. We don't need the maximum value in this case. We only need the minimum value. The minimum value is going to be 0 of any force, right? If you ask me what is the minimum value of any kind of force, I would say the minimum value is going to be 0. Maximum value, well, I may need to figure it out. So that's the minimum speed at the top, right? And then figure if this is 0, then it's very easy to find out the minimum speed at the top. Now, but in this question, we're not interested in the minimum speed of the ball at the top. We're interested in the minimum speed of the ball at the bottom. Well, if you repeat this experiment, you have found the minimum speed at the top. It can barely make to the top. So in this experiment, the speed at every point is going to be the minimum speed of the ball at that point in order to complete this circle, right? Because that's the minimum speed you can use to still finish this circle. So at every point, that will be the minimum speed in order to complete the circle. So that means in this experiment, if I already found the minimum speed at the top, then in this experiment, the speed at the bottom will be the minimum speed of the ball in order to complete this circle. So from the top to the bottom, then, because the acceleration is not a constant, forces are not constant, because the tension is not a constant. So it's not a very easy motion, but we can always use conservation of energy. So I'm just going to call this initial, this final, right? And then I can use conservation of energy from initial and final. Once I have found the initial speed, so that's going to be the initial speed. That's the first step, right? This is the initial speed. Initial speed is it's going to be the minimum speed at the top. Once you have found that, you can go ahead, set up conservation of energy using this, the top of the initial, the bottom as the final. Then you can find the minimum speed at the bottom, right, which is the V final. So if you set up conservation of energy, you always start with the same equation, the same law, and then write out every term. The left-hand side is always easy to set up. Okay, I don't even need the detail from the problem. I can always write change in kinetic energy as 1/2 mVf squared, right, minus 1/2 mVi squared. And the gravitational potential energy, I don't need the detail from the problem. I can write down these two terms. And the elastic potential energy is associated with the spring. In this question, there's no spring, so I'm going to put a 0 there. We will see some problem with the spring later, but right now there's no spring, so that's good. I have a 0 here. Now you're going to figure out the external work. The external work is the work from any force outside the system. So you're going to draw a Fibber diagram of this object and figure out how many forces are coming from the outside. I just drew these two forces, right? Gravity and tension. Gravity, you never worry about it in conservation of energy on the right-hand side, because we already considered the gravitational potential energy from gravity. So we already included the effect of gravity on the left-hand side. Gravity is already in our system. So this guy, never worry about it. And tension is going to be the force from the outside. And the tension is very tricky, right? Because the tension actually changes direction. If you draw the Fibber diagram at this point, this gravity is still down with the same value, but tension is going to become in that direction. So at every point, the tension changes direction and magnitude. You can't even predict the magnitude. So looks like it's very complicated, but remember, we did a question, right? This is similar to the pendulum question with that. This is a special question, well-designed question for this class, because at every point, the tension is always perpendicular to the displacement, right? So the displacement at this point, if I draw the very, very small displacement, it's going to be tangent, so perpendicular. What is the direction of the displacement at this point? Tangent, perpendicular. So at every point, the tension, because the tension is always toward the center, so it's a radius in the radial direction, and the displacement is always at the tangent direction, right, at this point, I would draw still the displacement this way, but the tension still radial. So always 90 degrees, always 90 degrees. So the tension is from the outside, but this is very similar to the pendulum question we did, but it doesn't do work because it always makes a 90-degree angle with the displacement. So the work from tension, right, it's going to be 0 because the angle is always going to be 90. You have a cosine 90. If you use the definition work is always force, displacement, cosine theta. All right? So then I don't have any work from the outside. So I'm going to put a 0 on the right hand side. Okay, it's very nice. Then the initial speed is going to be this speed I found using still Newton's second law in circular motion. And then I'm trying to find the final speed at the top, so I'm going to leave it there. And then final height and initial height, I don't even care where the ground is. I have two heights, right? This is the initial height, this is the final height. I can pick any of that as my 0 reference, right? So usually we will pick the lower one as our 0 reference to get rid of negative numbers because people are so afraid of negative numbers in physics. So why don't we just call this HF 0? So I would say this is where I set up my coordinate system, right? I'm going to draw my y-axis in this and call this my origin. So what if this is 0, what is HI? HI is higher than HF, right? What is the vertical height? You know that because you already know the length of this string. All right, so that's how you find the HI and HF. And then you can also see that the mass is going to cancel because every term has mass. You can divide every term by mass, so you get rid of mass. Then you will have all the numbers you need. VI, HF, HI, little g constant. You rearrange this equation, you can find the minimum speed of the ball at the bottom, which is the V final. Okay, so now you can pause the video, finish that draw, and then see if you can get the right answer. All right, so let's first figure out this guy. So this we have done that in the circular motion, right? If you make this tension 0, that's the minimum. So you only get mg equals mv squared over r. And then that's just going to give you, so that's your VI. This VI, and then you can just leave VI squared because at the end you just need VI squared to plug in. So VI squared is g times r. Okay, I'm not going to calculate the number here. I always plug all the numbers in at the end because when I manipulate this equation, I may cancel some symbols, which can make my calculations easier. Okay, and carrying symbols to do algebra is less likely to make a mistake when you carry a lot of numbers. A lot of people, when they move numbers around, okay, copy numbers from their calculator or enter numbers in their calculator, they make a mistake. Okay. So I would always work with the symbols first. So if you divide every term by mass, you will get this, right? Plus GH final minus GHI equals 0. And then what is the HF and HI? HF we just said, I'm just going to assume is 0. That's my 0 reference. If I assume the final height, the bottom is 0 height, then the initial is just going to be the radius 2r. That's the vertical height between these two points. Then you see that you can plug out all the numbers in, right? So 1/2 VF squared equal minus 1/2. Now I can replace VI squared as this. And then this is 0. This is g times 2r. Now you can move everything terms around. You can find this VF, right? At the end, the VF I found. So at the end, you only need to plug in g and r. You can even combine these two terms, right? Move them to the right. So the VF, what is the final speed that you got? The final speed I got is 4.4 meters per second. All right, so very nice. Even though the motion is very complicated, not a constant acceleration motion, you can always use conservation of energy, set up the initial and final work from the outside in this process. Then you go ahead and rearrange this equation. You should be able to find out what you need. All right, let's move on to the next question. Let's take a look at this question. So it's a new story. Let's read it. It's been a great day of new snow. Okay, good to know. Julie starts at the top with a 60-degree slope shown in the figure. Okay. At the bottom, a circular arc carries her through a 90-degree turn, and she then launches off a 3.5-meter high ramp. If the friction force from snow is negligible, which is a valid assumption, right? What is Julie's speed when she leaves the ramp? Okay, I don't care if it's a person, a ball, a car, or whatever is moving, right? It's an object. So the question is this: an object, it's moving on this track. So it's a slope, and then with an arc. Okay, so it looks very complicated. But again, if I see a very complicated motion, I would try conservation of energy, because I know that conservation of energy can help us solve very complicated motions. I don't even need the detail of this process. I just need an initial final, and then final work in this process. Now let's see. So an object slides down, right, a slope, and then there's a arc, there's a 90-degree turn, so then this becomes an arc, and then she's going to launch off at this point. So I know that at this point she's going to be moving that way, right? And then after that, that's going to be a projectile motion, right? Okay, but I'm interested in the speed of this person at that point, or this object. It's an object to me. Now this object starts from the top, and then I want to find the speed at this point. So it looks a very complicated process. I'm going to use conservation of energy instead of Newton's laws and kinematic equations. So I'm going to still set it up this way. Let's see, final minus initial kinetic energy. Good. Final minus initial gravitational potential energy. Good. What about the elastic potential energy? No, there's no elastic potential energy in this process, so I still get a 0. What about this guy, right? See, the left-hand side never changes. You always have final minus initial, final minus initial, final minus initial. So that's why I really prefer these conservation laws than Newton's laws and the kinematic equations. Okay, because you always set up the same way. So for right-hand side, you're going to draw a three-body diagram of this object. So let's draw it. So the person is going to have its own gravity, right, always. And then there's a normal force in this direction. So because the problem says that let's forget about friction. The friction is negligible. So there's nothing else, only these two forces. Okay, so gravity, you never need to worry about it. Okay, it exists, it does work. Of course, you see that it's there, and then it has a displacement, has an angle. But I don't consider it from the outside. It's already in my system, because I already defined gravitational potential energy. So the only thing I need to consider is going to be normal force. But now you see that if I want to calculate the work done by normal force, in this question, I would do normal force again times displacement times cosine theta. So even if the path is really complicated, I can still break it into different parts and calculate the work done in each part, right? So on this part, you see, if this is the slope, the direction of the displacement is going to be in this way. And what is the angle between the normal force and the displacement? 90 degrees. Okay, oh, I have done several problems with 90 degrees between the force and displacement. The cosine 90 is always 0. So it's not doing work. Okay, very nice. I will get a 0 for the normal force. Some people may say, oh, what about when the person reaches this arc, this circular track? Well, again, that's pretty much like the string, the pendulum, and this vertical circular motion we just saw, right? At this point, at any point, the tension, if this is an arc, the center is here. The normal force is going to be, if this is center, the normal force is going to be toward the center because it's perpendicular to the surface. But the displacement is always tangent to the surface. And again, these two forces, they're going to make a 90-degree angle, right? For example, if you draw the Fourier diagram here, normal force perpendicular to the surface, but the displacement at this point, it's going to be parallel to the surface. So again, 90 degrees everywhere, all the way through 90 degrees, because normal force is always perpendicular to the surface, and the displacement is parallel to the surface, right? In this case, if it's moving along the surface. So I still get a 0 for the work done by normal force. Again, because this is a well-designed problem for this class, okay? So I still get a 0, because calculating work for an arbitrary force and an arbitrary displacement can be tricky, okay? So the problem we see in this class, they're gonna still be well-designed so that it's gonna be very easy to calculate the work done, okay? So see that nothing has changed, nothing has changed. Then you can divide every term by mass, nothing has changed, right? So only after this step, you're gonna plug in different numbers, right? So as I said, I really like conservation laws, okay? They're actually, once you get used to them, they're actually easier to apply than Newton's laws and the kinematic equations, because you don't need to worry about the detail of this process. So let's see. So this is my final point. This is going to be my initial point. So I'm trying to find a VF. So I'm going to leave VF in that equation, right? What is VI? Well, if she starts at the top, so she's going to start from rest, right? When she starts skiing. So VI is going to be 0 at this point. Now, what about these two heights? Then if I have these two heights, I can go ahead and rearrange that equation. I do have these two heights, right? The problem says this is 3.5 meters, so that's going to be my final height to plug in. And then it says this height is what? 28 meters. All right, you see, nothing has changed. Nothing has changed. I just plug numbers in and rearrange this equation, right? Because VI is 0, so I will have this. And then move these two terms to the right, you will get negative GH final plus GH initial. Now you can plug all the numbers in. You can find the VF, right? Pause the video, finish the algebra. Okay, so what is the speed? This is 21.9 meters per second. And this is actually a very large speed. If you convert it to miles per hour, that's like about like I guess around 50 miles per hour. So skiing, it's really dangerous. You see that you can get like a speed really large. So you should be really careful if you want to go skiing. Okay, see that physics is useful. Okay, we have finished this question. Let's move on again to another question to do more practice. So in this question, we will have some term on the right, right? For these two questions we just saw, we got a 0 on the right hand side, but it's not always 0, right? If there is a force from the outside doing work, you just need to consider that. And you don't need to remember some rules, right? Some people, they always want to remember, like if there's just any rule that I need to remember so that it can help me predict. For this question, I need to calculate the work. For that question, I get a 0. I don't like memorizing rules and shortcuts and conclusions, right? I just use the definition. I do need some experience. That's why we are doing this practice. I do need some practice, right? I need some experience. For example, we have done questions with the force and the displacement makes it 90 degrees, so that's going to be 0 work. So next time if I see some force and displacement like that, okay, I don't need to remember that, right? I have some experience, so if I draw these two vectors and I realize the angle between them is always 90, so that's going to be 0. But I don't need to memorize anything, right? I still set up the work definition, and then if the theta angle becomes 90, I will get a 0 work. So let's take a look at this question. Okay, so a 5 kilogram crate slides down a ramp from rest at the top. Okay, good. The ramp is 2 meters in length, and then inclined at an angle of 30 degrees. Okay, so I know the length of the ramp, the angle of the ramp, the coefficient of kinetic friction between the crate and the ramp is 0.5. So I know this mu k, right? So I believe that's going to help me find the kinetic friction force, right? We want to find the speed of the crate at the bottom of the ramp. Okay, let's draw it out. So this is the ramp. The crate is going to start from the top, it's going to slide down, and then we want to find the speed of this crate at the bottom. So that's what we want to find, and that's the ground. What do we know? We know this mu k from the problem, right? Mu k is 0.5. Okay. We know the ramp has a length 2 meters. This is 30 degrees, right? And then we want to find the speed of the crate at the bottom. Okay, so let's set up conservation of energy again. If I set up conservation of energy, no change, no change, no change, because there's no spring in this problem. The right-hand side, again, the right-hand side totally depends on the problem. You do need the detail from the problem. So let's take a look at the right-hand side. You're going to draw a Hilbert diagram of this object. So in this case, it's going to be gravity again, normal force, and in this case, I should consider friction force, and this kinetic friction force in this direction. So these are the 3 forces on this object. Now let's see. Do I need to calculate any work in this process? Gravity, you never worry about it on the right-hand side, right? We have done that many times. Normal force, okay. Normal force is perpendicular to the surface, but what's the direction of the displacement? Parallel to the surface, okay? I just saw a problem with this condition, right? If the force makes a 90 degree with the displacement, that's going to be 0, because you always get a cosine 90, okay? So the work done by normal force in this case is 0. Nice, very good. Again, I'm not going to remember the shortcuts, right? And next time I see a normal force, the work done is 0. I don't even need to read the problem. What are you doing, right? Are you really trying to solve this problem, or you're just trying to memorize some shortcuts and conclusions? You can solve the problem without even thinking. Think about it, right? That's not what we're doing, right? I still want to draw a Hilbert diagram and then use the laws and theories I learned to solve this problem. That's what we learn. Then this guy is 0, okay? Only because it makes a 90-degree angle with the displacement. Now friction force, you're going to calculate that. And friction force, you're going to do force times displacement times cosine theta angle. And what is this theta angle? This theta angle is going to be the angle between the force and displacement, and this is 180. This is not 0, right? Because one is in this direction, the other one is that one. So this is the work. So I should put this number on the right. So I do have one number on the right to calculate the work done by friction force, okay? But everything else is going to be the same. So, okay, so after that step, everything has changed. So I'm trying to find the final speed at the bottom, okay? So I'm gonna leave it there. What is the initial speed? Well, okay, it starts from rest, good. So the initial speed is still 0 at this point. So this is my final point. This is my initial point, right? So initial speed is 0. Do I know these two heights, right? If I know these two heights, then I'm good on the left-hand side. The only thing I don't know on the left-hand side is the final speed. So I don't need to worry about the left-hand side. Again, now we do have a ground, okay? So most people will just say, I'm just gonna call the ground 0 height, okay? So this is gonna be the final height I plug in, because it's already the ground. What about the initial height? Initial height is this point, right? So you need the vertical height. The problem doesn't give you the vertical height, but you have a right triangle to use here, right? You have the hypotenuse, you have the angle, you can find this vertical height, right? So that's the HI you can plug in, okay? So that's how I'm gonna find the HI. So there's one number I need to find on the left-hand side, but I know how to find them. What about the work done by the friction? Do I have all the numbers for this equation? If I do have them, so I don't need to worry about the right-hand side. The rest just gonna be algebra. The friction force, okay, you don't know the friction force, so you need to find the friction force. But how do you find the friction force? Friction force has a equation, mu k times the normal force, right? So mu k is given. That's why the problem gives mu k. So I just need to find normal force. But in this case, you shouldn't just write normal force equals gravity. Don't make that mistake, okay? Don't remember the shortcuts, okay? You need to use the Freiberg diagram to find the normal force, right? And we have done that many times. So let's just draw it again. So gravity is down, normal force perpendicular, okay, friction force parallel. And then how do I find the normal force? I still need to use Newton's laws, right? So on the incline, I would draw a coordinate system this way. This is x, this is y, right? That's what we do on an incline. If I use this x and y, so I can set up so I only need to find normal force. So let's take a look at the y direction. And because the object is not moving in y direction, so I would have the net force in y direction is going to be the sum of all the forces in y direction. That must be equal to AMAY. So then you see that we have done that before. You need to break gravity into x and y components, but in this case, we only need the y components. Okay, so you will just get normal force minus mg y component, right, equals 0 because there's no acceleration in y direction. Then how do you find y component? We also did that earlier. So if this is the inclined angle, theta, okay, which angle is theta? If you want to transport angle theta in this right triangle, this angle is theta. We've done that many times, right? You extend some line, you see that. You can use all these right triangles to figure out that theta. If you still don't know how to do that, try it again. You can always find which angle is theta. So that's going to help you write this mgy in terms of mg and cosine theta, right? Okay, so you see that you will be able to find normal force using this Newton's second law, still Newton's second law. And once you have normal force, you can find friction force, and then you plug it in. What about the displacement? Well, this displacement is just going to be the length of the ramp, right? Because it's just going to slide down the ramp. Okay, so now I have all the numbers on the right. I have all the numbers on the right. I have all the numbers on the left. You just need to calculate this HI, right? Then I'm confident the rest is just algebra. Okay, actually I have already set up this problem as a physics problem. I'm just going to do the algebra. Okay, so now you can pause the video, finish the algebra. Okay, so let's see. Again, I'm going to work with the symbols first. So this guy, as I said, if you figure out which angle is theta, this is going to be mg cosine theta. Right? So the friction force is just going to be mu k mg cosine theta, right? So the right hand side is going to become mu k mg cosine theta, that's the force, times the displacement, which is just going to be the length of the ramp, so let's call it L, and then times another cosine 180, okay? That's the right hand side. The left hand side, let's see, 1/2 mvf squared minus 0, okay, plus, this is also a 0, because I call it a final point my 0 reference point. Now the initial height is going to be mg, okay? If you want to find initial height, you can do the length times the sine 30, because this is opposite, right? So the initial height is going to be whatever the length is times sine theta, okay? So L sine theta. Now you see that you can move this term to the right 1/2, okay, erase this. Mvf squared equals mg L sine theta minus mu k mg cosine theta L cosine 180. Now you're ready to plug numbers. You can even cancel little m. You see that the mass, you don't need the mass on, you can divide each side by the mass, right? But anyway, the rest is just algebra. You rearrange this equation, you will find this VF. It's going to be equal to this whole thing, GL sine theta, because m is going to cancel, minus mu k g cosine theta L cosine 180, okay? Oh, this is a plus sign, I'm sorry. Why do I change it to negative? This is a plus sign, okay? And then this whole thing divided by 1/2, which is going to become a 2 at the top, in front of it, right? So, and then square root this thing. Okay, this cosine 180 is going to become, this is going to give you a -1, right, if you plug numbers in. But this is going to be the complete expression. So now I can plug numbers in. What is the number you got? And theta angle is 30 degrees, right? The number I got is 1.6 meters per second. Okay, so that's how we solve this problem, still using a conservation of energy. Okay, let's take a look at the next one. Now we're going to see a problem with more than one object. Okay, if you have more than one object, you just need to, the only difference is you just need to calculate these 3 terms for each of them. Okay, and also the work, you're going to take a look at the work done on each object. So it's you're going to get more terms, but the theory is still the same. Right, that's what we're learning. We always use the same theory, the same law to solve different problems. Take a look at this question. Block of mass, okay, 3 kilograms connected to a ball of mass 5 kilograms by a string. There's some friction force between the block and the table, and the mu k is 0.5, right? The ball is 0.4 meters from the floor. It's going to be released from rest. We want to find the speed of the block when the ball reaches the floor, okay? Again, let's draw it out. Okay, so the block is on a table, and then it's attached to a string. Okay, it's attached to M2 with a string over this pulley. So this is M1, this is M2. And then this guy has 0.4 meters from the ground. Okay, this is the ground. Now we're gonna just release M2 from rest, right? Once you release M2 from rest, if M2 is heavy enough, so it's just gonna pull M1 to the right and M2 is going to drop. So that's why M2 is going to hit the ground at the end, right? So we just want to find the speed when M2 hits the ground. So, okay, it looks like a very complicated process. I'm going to set up conservation of energy. Okay, let's do that. So if I set up conservation of energy, I'm going to, now I have two objects in the system. Now I'm going to find out changing kinetic energy, changing gravitational potential energy for each of them. But I still don't have elastic potential energy here because I have no spring. So I will write out every term without using any detail from the problem. Right? That's the beauty of these conservation laws. It's for the M1, then do the same thing for M2. Okay, so that's data K. I got 4 terms, that's fine, right? I just got more terms. I'm not using a new theory. Now M1G, let's do gravitational potential energy. All right, and do the same thing for M2. And then I still don't have any elastic potential energy, so I get a 0. Okay, so that's the left-hand side. Okay, that's the left. It looks very scary, but in this problem we see in this class, usually we get many zeros. We will get many zeros in this equation. So you don't really need to work with 8 terms. Okay, we can figure out each term carefully. Now let's take a look at the right-hand side. So on the right-hand side, you can consider all the forces from the outside. Draw a Hilbert diagram for each object in this problem. Let's draw a Hilbert diagram for M1. Gravity, normal force, and then friction force. And then there's a tension. Right. Draw a Hilbert diagram for M2. M2 easier because it only has gravity and tension. Okay, so let's take a look at M1. So if I want to calculate the work from outside, external work on M1, so you need to calculate all the external work on M1 and all the external work on M2. So that's the external work on this system. They're going to put all of them on the right-hand side. Okay, so you can't predict how many terms you're going to have on the right-hand side. Just do that for each force, right? You don't need to remember any rules or any conclusions or any shortcuts. M1, okay, this guy, never worry about it, right, on the right-hand side. And then the normal force, okay, I've done that with many problems. If this is a displacement for M1, well, normal force and the displacement makes 90-degree angle, okay, it's going to be 0, the work. You see that once you have done a lot of practice, you have gained a lot of experience, you will get a little bit faster, okay, you will get a little bit faster. That's why we practice before the test. Now, normal force, I get a 0. So the tension, well, now you see that I'm going to consider M1 and M2 as a system. So this string is just between them. So the tension is some force inside the system, like gravity. Okay? So the tension, I don't need to worry about it. Okay? You don't even need to worry about it at all. You don't even need to figure out if the tension is making a 90-degree angle or whatever. No, it's inside my system. I don't need to write it on the right-hand side. That's the beauty of conservation of energy. I don't need to worry about what things happening inside my system, which can be really complicated. I only need to worry about the effect coming from the outside. So the only work I need to calculate for M1 is going to be, again, the friction force work. And we have done that before, but I don't need to remember anything, right? It's always going to be force, displacement, cosine, and then theta. That's the definition. I'm just using that definition. And how do you calculate the friction force on M1? That's going to be mu k, normal force, right? And the normal force in this case is very obvious because in y direction, I only have normal force gravity y direction, they must be equal. So this is how I'm going to calculate the kinetic friction on M1. So okay, so that's going to be something I'm going to put on the right hand side. The work done from the friction on M1. So I'm done with M1, right? You see, there are 4 forces on M1, but the only work I need to calculate is still going to be the work done by friction. Take a look at M2. Gravity, never worry about it. Tension in my system. So both of them are already in my system. So you don't need to write any external work for M2, right? So you only need to calculate work done by friction on the right hand side. Okay, and then we know how to calculate that, right? This is how I'm going to calculate that. So I do have all these numbers, and the angle, what is the angle between the friction and displacement? This is like what we just saw, right? So you know the angle. But I don't have the displacement. Well, think about it, right? The problem says that M2 is going to fall to the floor, so M2 is going to move down 0.4 meters. If M2 falls down 0.4 meters, how much distance does M1 move to the right? It's going to be the same, right? So you know this number. This number is going to be equal to the height of M2. So you know all the numbers you need for friction force. Okay, good, okay. Now I'm going to worry about the left-hand side, okay. I'm going to set up everything, okay, until I'm sure that there's only one variable in this problem, okay. Then I'm going to go ahead and do the algebra. Take a look at these two speeds. Initial speed is 0, so I will get an initial speed 0, so this term becomes 0, right? Because everything starts from rest, the problem says. So V1F, okay, I'm going to leave it there because I'm trying to find V1F, like the problem says find the speed of the block. Leave it there. Now M2, again, M2 is going to start from rest. So I already got 2 zeros, as I said. Usually there will be many zeros in these problems. So even though you set up this problem with a lot of terms, don't be scared. You will get many zeros. And then V1F and V2F, looks like they are 2 different variables, but they are the same variables because M1 and M2, they're connected. They will have the same speed. They will always cover the same distance if the string doesn't break. Right? They will always cover the same distance in the same amount of time, so they will have the same speed. They will also have the same acceleration, even though the direction can be different, but the values are going to be the same. So V1F and V2F, they're actually going to be one variable, so I'm just going to call it VF. Okay, so I still have a VF after these 4 terms, so okay, that's good, and VF is what I'm trying to find. Now take a look at these 2 terms. M1. M1, I don't know the height of this table, so it looks like I'm missing the height for M1. But do you really care? You don't, because M1, the height is not changing, right? Whatever the height of the table is, H1F is going to be equal to H1I, because the height is not changing. So you don't need to calculate any change for M1, because this whole thing, this is going to be always equal to that term. These 2 terms are always equal, so you will always get a 0. Okay, you see that? Now I got rid of 2 terms together. Now take a look at these 2 terms. So M2 is falling, so it will have some final and initial heights. So again, because this is a floor, why don't we say this is 0 height? If this is 0 height, this is going to be the initial height for M2. So I have this guy and another 0, right? So you see that I crossed out 5 terms, right? I'm only left with 3 terms on the left. I started with 8, okay? But I would always write out every term to show my work, right? I don't want to, you know, lose any credit, right? So and I can even add these 2 terms together, so they will just give me this. Because this is only one variable. And then I have this negative M2GH2I. You see that? Very nice. On the left-hand side, I only actually have 2 terms that left at the end, after I combine these 2 kinetic energy terms. Now the right-hand side is going to be mu k. We just figured M1G, that's the force times displacement times the angle, which is going to be 180 again. Again, it's not because I remember it's 180, I draw them out, right? Displacement in that direction, force in this direction, 180. And then these H2i and data R1, they're the same, right? Now you see that I have all the numbers I need. I will go ahead and solve this equation to find a VF, okay? Now you can pause the video, finish the algebra, okay? So what is this VF? So at the end you will get this, right? You rearrange this equation, what do you get? You move this term to the right, you get M2G H2I plus mu K M1G data R1 cosine 180 okay, don't forget the square root. Now you can plug numbers in because these two numbers, they're just going to be both 0.4 meters. You plug all the numbers in. The final answer, what is the final answer you got? Final answer I got is about 1.9 meters. Okay, so this is this question. I'm going to stop here for this video.